For decades, scientists have been relentlessly pursuing the goal of developing aircraft capable of traveling at light speed, a velocity that could potentially unlock answers to some of the most profound questions of human existence. Questions like, how did we come to be? And, what lies beyond our reach in the vast expanse of the universe, linger in the minds of researchers and dreamers alike. With NASA's latest advancements, this ambitious dream might one day become a reality. In this discussion, we'll explore the cutting-edge discoveries made by NASA and examine what these findings might mean for the future of space exploration. First, let's define what light speed actually is. As the term implies, light speed refers to the speed at which light travels through a vacuum, a staggering 671 million miles per hour. This unimaginable speed is the maximum rate at which any form of energy, matter, or information can theoretically move. According to the laws of physics, only electromagnetic waves like light, radio waves, and gamma rays are capable of reaching light speed in a vacuum because they lack mass. These massless waves face no resistance or interference in a vacuum, allowing them to travel freely and unimpeded. On the other hand, particles that do possess mass, such as protons, electrons, and atoms, can never achieve light speed, no matter how much energy is applied to accelerate them. This intrinsic limitation is why light speed serves as a natural boundary, setting the fastest possible rate of travel in our universe. Even the fastest spacecraft humanity has created, such as NASA's Parker Solar Probe, which launched in 2018, only reaches a fraction of this speed at 430,000 miles per hour. Historically, NASA's efforts in space exploration have focused on maximizing speed within the confines of our solar system. Spacecraft like the Parker Solar Probe and New Horizons achieved remarkable velocities by using gravitational assists, relying on the pull of nearby planets to propel them forward. NASA has also researched new propulsion technologies to push the limits of space travel, such as ion thrusters, solar sails, and even antimatter propulsion systems. However, none of these technologies come close to light speed, and even if they could, they currently lack the capacity to carry human passengers. In addition to propulsion innovations, NASA has explored other theoretical ideas in physics and cosmology, such as wormholes, hypothetical shortcuts through spacetime that could, in theory, enable faster-than-light travel. However, these concepts remain largely speculative and unproven. In recent years, though, NASA has been exploring fresh approaches to overcome the light speed barrier, turning its attention to the concept of manipulating spacetime itself. This cutting-edge research draws upon the theories put forth by Dr. Harold Sonny White, who in 2012 proposed warping the very fabric of spacetime to create a warp drive effect. To pursue these ideas, NASA established the Advanced Propulsion Physics Laboratory, commonly known as EagleWorks, at its Johnson Space Center. Led by Dr. White, this facility focuses on pioneering propulsion technologies, including those that might one day enable faster-than-light travel. The laboratory conducts experiments in extreme environments, develops advanced propulsion systems, and investigates theoretical physics topics like wormholes. Initially, the energy requirements for light-speed travel were thought to be astronomical, requiring energy many times greater than that of the entire Sun. However, over time, researchers have reduced this estimate to a more manageable level, even proposing that the energy needed might be closer to the mass of Jupiter. Dr. White's concept involved creating a warp bubble that could theoretically enable travel to nearby stars like Alpha Centauri within a few weeks at an energy cost comparable to that of an average car. NASA's EagleWorks laboratory has made some promising strides in these areas. For example, they have constructed an instrument called the White-Jude Warp Field Interferometer, designed to measure minuscule changes in spacetime, potentially critical for this kind of advanced travel. While some positive results have emerged, scientists still face significant challenges in scaling these technologies to power an actual spacecraft. Following Dr. White's initial work, NASA engineer David Burns proposed a bold new concept for an engine capable of light-speed travel without propellant. Inspired by the controversial M-drive, an idea first suggested by Roger Shawyer in 2001, Burns' engine concept, dubbed the helical engine, relies on principles from special relativity to achieve thrust. The M-drive, a propulsion system that produces thrust without traditional fuel, defies current physical laws and has often been dismissed by mainstream scientists. Despite this skepticism, some tests have indicated the M-drive could indeed produce thrust, though the exact mechanism remains unknown. Building on this groundwork, Burns' helical engine would use particle accelerators to accelerate ions and exploit changes in mass at near light speeds to generate propulsion. If successful, the helical engine could potentially revolutionize space travel by enabling spacecraft to travel at unprecedented speeds while minimizing fuel requirements. Berne's concept employs a series of springs within a looped system, using special relativity to manipulate ion mass and create directional thrust. As the ions accelerate, they gain mass, producing a larger force and greater propulsion in a specific direction. Although the concept sounds promising, the engine would have to be massive, about 200 meters long and 12 meters wide, and require 165 megawatts of power to generate just 1 newton of thrust. Such an engine could only operate effectively in the frictionless environment of space. Despite these advancements, researchers acknowledge that a light-speed engine faces numerous physical, environmental, and even ethical obstacles. For one, traveling at light speed would produce extreme time dilation, meaning time for the astronauts would slow down relative to time on Earth. This could have unforeseen consequences for a space crew, such as aging more slowly than people on Earth, causing serious isolation challenges and physiological impacts. Additionally, light-speed travel would introduce formidable navigation issues. The immense velocity would make it nearly impossible to detect and avoid obstacles, such as other celestial bodies, potentially leading to disastrous collisions. The energy demands for reaching such speeds could also distort spacetime, potentially creating ripples that affect nearby cosmic structures. A light-speed spacecraft, however, could redefine our understanding of the cosmos and offer unparalleled research opportunities. Scientists could directly study phenomena that were previously only observable from afar, including black holes, dark matter, and dark energy. Observing these objects up close would deepen our understanding of fundamental physical laws and could even reveal new ones. Such a vehicle would also open doors to examining the origins of the universe, investigating the Big Bang, and providing insights into the earliest moments of cosmic history. While the concept of a light-speed engine remains largely theoretical, Burns encourages an open-minded approach to radical ideas, reminding us that aerospace innovation has often involved overcoming the impossible. Though the science of the M-drive and the helical engine is still uncertain, the relentless advancement in aerospace technology might just lead us there. After all, there was a time when the idea of humans flying in airplanes seemed equally unfeasible.